Welcome to this explainer on feedback systems in control system theory. We're going to take a really enthusiastic, deep dive into the hidden mathematical engine that governs nearly everything around us, from the precision robotic arms in industrial automation and the exact trajectory of drones, all the way down to the cruise control in your car. Feedback is literally the silent force making modern engineering possible. Okay, here is our agenda for today. 1. The control systems around us. 2. Open versus closed loop systems. 3. The anatomy of feedback. 4. Deriving the transfer function. 5. Performance and disturbance rejection. And finally, 6. The cost of feedback. Let's just jump right in.
Section 1. The control systems around us, hidden in plain sight. Think about it for a second. From pointing these absolutely massive antennas at distant stars, to modern electric vehicles managing their battery temperatures, or even, your own body regulating its blood sugar, control systems are simply assemblies of components designed to hit and maintain desired targets. They take an input, process it, and aim for a very specific output. But, as we'll see, not all of these systems are created equal.
Section 2. Open versus closed loop systems. Adding measurement.
This elegantly highlights the core problem we face as engineers. An open-loop system like your basic toaster runs totally blind. It toasts for 2 minutes, regardless of whether the bread is thin, thick, frozen, or already burned to a crisp. It just doesn't know what's actually happening. On the other hand, a closed-loop system, like a modern smart oven or a thermostat, actually measures the reality of its environment and adjusts its actions on the fly to get the exact result we want.
So, the absolutely crucial point here is that a closed-loop system is actively measuring its own output and feeding it back to compare against the desired goal. This comparison creates what we call an error signal, which tells the system exactly how much it needs to correct itself. That error signal is the magic that allows systems to handle unexpected disturbances.
Section 3. The anatomy of feedback. Building block diagrams.
I absolutely love this piece of history. This is a famous 1927 eureka moment from engineer Harold S. Black. While riding the Hudson River Ferry, he was pondering how to reduce distortion in telephone signals. He suddenly realized that by feeding it output back into the input in reverse, basically subtracting it, he could beautifully cancel out the system's own distortion. That single ferry ride practically birthed modern control theory.
Now, when we build these systems graphically, we use block diagrams with some very specific vocabulary. We have the plant, which is the actual physical process we're controlling, like a DC motor. We have the sensor, measuring the actual output. We have the summing junction, calculating that error we talked about. And finally, the controller, which takes that error and tells the actuator exactly how hard to work to fix it.
You absolutely must remember that negative feedback is actually the hero here. It subtracts the output from the input to stabilize the entire system. Positive feedback, on the other hand, adds the output right back to the input. Think of a microphone getting way too close to a speaker or economic inflation. It compounds on itself and can lead to really dangerous runaway instability.
Section 4. Deriving the transfer function. The mathematical engine.
To model these dynamic systems mathematically, without getting totally bogged down in brutal, complex differential equations in the time domain, we use the transfer function in the Laplace domain. By transforming our variables into the S domain, complex calculus literally turns into simple algebra. It makes analyzing the whole system infinitely easier.
Let's actually walk through this derivation step by step. First, we start by defining the error signal at the summing junction. E of S equals the reference input minus the measured feedback. Then we push that error through our forward path, the plant, to get our output, C of S. Finally, we just algebraically substitute the first equation right into the second and solve for the ratio of the output to the input.
And boom, that brilliantly illustrates our final closed-loop transfer function. The output over the input equals the forward gain G of S divided by 1 plus the loop gain G of S times H of S. Seriously, if you're going into automation or control engineering, print this out and frame it. This is the absolute cornerstone equation of modern control theory.
Section 5. Performance and disturbance rejection. Surviving the real world.
Look, in an ideal theoretical world, an open-loop system might be fine. But in the harsh reality of the real world, open-loop systems fail dramatically. A DC motor suddenly encounters load friction, or a massive radar antenna gets hit by a chaotic 50-mile-per-hour wind gust. Without feedback actively checking the output, these systems deviate entirely from their commanded paths and just fail.
By evaluating our closed-loop transfer function, we find that increasing the loop gain mathematically shields our system. It's like armor. It decreases the system's sensitivity to its own internal wear and tear, it powerfully rejects those external wind gusts and frictions, it attenuates measurement noise, and it dramatically reduces the steady-state error.
When we run the numbers from a standard engineering simulation, you can see the sheer power of this math. By simply closing the loop on a system, the steady-state error, that lingering inaccuracy after the system settles, drops from 1.1% down to 0.011%. That is a staggering 2 orders of magnitude improvement just by adding a feedback loop.
But wait a second. With all these incredible benefits, from pinpoint accuracy to robust disturbance rejection, we have to ask ourselves a really fundamental engineering question. What exactly are we paying for this magic? Because in physics and engineering, nothing is free.
Which brings us to Section 6, the cost of feedback, engineering trade-offs.
Because adding feedback means you're purchasing and integrating expensive sensors, which right off the bat increases system complexity and cost. Furthermore, sensors aren't perfect. They introduce their own high-frequency electrical noise right into the system. We also intentionally sacrifice overall system gain. But worst of all, we risk the stability of the entire process.
And this right here is a control engineer's absolute nightmare: instability. If you introduce a time delay into your feedback loop, or if the system's mathematics shift out of balance, your perfectly stabilizing negative feedback can accidentally invert. It becomes destabilizing positive feedback. This leads to violent physical oscillations, literally tearing machines apart, much like an auditorium microphone screeching totally out of control.
I'm going to leave you with a provocative thought to ponder. Feedback systems give us the illusion of perfect control. But as we build increasingly complex, AI-driven autonomous systems, like self-driving cars navigating chaotic cities, who controls the controller when the physical environment inevitably exceeds the bounds of our mathematical models? Thanks so much for joining me on this explainer, and keep questioning the systems around you.